Vector spaces. In this lesson, we review the theory of vector spaces. This lesson provides the terminology and concepts necessary to move from solving simple linear systems to using linear algebra as a formidable tool. In earlier lessons, we thought of vectors as n by 1 matrices. While such an interpretation is useful, it ultimately limits the scope of linear algebra. Later, we will construct a broader algebraic definition for a vector. For now, think of a vector as an object that can be added to another vector and multiplied by a scalar. Suppose that we have a set Q of vectors. We say that W is a linear combination of the elements of Q, if W is the sum of scalar multiples of the vectors Q. Of course, by setting all the scalars to 0 we get the zero vector. A vector space V of Q is the set of all possible linear combinations of vectors in the set Q. We say that V is the span of Q, a noun, and the Q spans V, a verb. It should be clear that the zero vector is in every vector space. Formally, we can define a vector space V as the set of all vectors possessing two properties. If a vector is in V, then any scalar multiple of that vector is in V, and if any two vectors are in V, then the sum of the two vectors are in V. If both properties hold, we say that V is closed under addition and scalar multiplication. Suppose that we take the objects x plus 1, 2x, x squared, and 4. We don't need to worry what x is. One arbitrary linear combination of these vectors is 3 times x plus 1 times 2x, plus 2 times x squared, plus 0 times 4. Another one is 7 times x plus 1, minus 3 times 2x, plus 0 times x squared, minus 3 times 4. And a third one is 8 times x plus 1, minus 2 times 2x, plus 5 times x squared, minus 2 times 4. And there are others. Let's simplify these expressions. It's not that difficult. Guess what the span of Q is from these linear combinations. The span of Q is the set of all quadratic polynomials ax squared plus bx plus c. The vector space spanned by Q is the space of quadratic polynomials. Note that although the set Q contains 4 vectors, it is really representative of only 3 vectors. The first vector is a linear combination of the second and fourth vectors, so it doesn't provide any additional information. We say that a set of vectors is linearly dependent if we can write any one of them as a linear combination of the others. This is the same as saying that there is a linear combination of the vectors which equals 0 without setting all the coefficients to 0. It is also the same as saying that any vector which is a linear combination of v1 through vn cannot be expressed as a unique linear combination of v1 through vn. A set of vectors, which is not linearly dependent, is said to be linearly independent. Such a set contains no redundant information. A basis of a vector space V is a set of linearly independent vectors which spans V. This means that there is enough information to fully determine a vector space, but there are not so many vectors as to make any one of them redundant. One can say that a basis is the smallest set of vectors that can be used to represent a vector space. Consider the vector space P2 of quadratic polynomials. One basis is the set of monomials 1, x, and x squared. Another one is x plus 1, x squared, and 4. And yet another is x squared plus 2x, and x squared plus 2x plus 1. The number of vectors in a basis is called the dimension of a vector space. The dimension of the quadratic polynomials is 3. Let's re-emphasize the following central idea of bases. For any non-zero vector space, a basis is not unique. In fact, for every non-zero vector space, there are an infinite number of bases. But once a basis is chosen, any vector in that vector space can be described by unique linear combinations of the basis vectors. This means that as long as we specify the basis, we can write any vector in shorthand notation as a column vector of coefficients. Once again, consider the quadratic polynomials. The usual basis for the quadratic polynomials is the monomials x squared x and 1. A vector 3x squared plus x minus 2 can be equivalently written in shorthand as the vector 3 1 minus 2. If instead, we choose the Legendre basis 1/2 times 3x squared minus 1, x, and 1. The same vector is written as 2 1 minus 1, because 3x squared plus x minus 2 is equal to 2 times the first basis vector, plus 1 times the second basis vector, minus 1 times the third basis vector. We say that W is a subspace of the vector space V, if W is both a subset of V, and W is itself a vector space. For example, let's consider the vector space P2 of quadratic polynomials again. What are some of the different subspaces of P2? Trivially, the vector space P2 is a subset of itself, and so is 0. The span of x squared plus 1 and x forms a subspace. In general, the span of any subset of vectors in P2 forms a subspace. Of course, the set of lines in the plane forms a subspace. By adding two lines, we still get a line. And the same is true if we multiply a line by any scalar. The set of constants form a subspace. They are also a subspace of the lines passing through the point 1, 0. If we add any two such lines, we get a line passing through the point 1, 0. And if we scale such a line, we still a line passing through 1, 0. So, what is not a subspace of V? The set of lines passing through 0, 1. If we add any two such lines, we'll get a line passing through 0, 2. Since this new line doesn't pass through 0, 1, it's outside the original set. This isn't a vector space, so this isn't a subspace. Lines with negative slope are also not a subspace. If we multiply such a line by -1, we get a line with positive slope. That's outside the set. A transformation A is a mapping from one vector space V onto another vector space W. Scaling a vector scales its image by an equal amount. Adding two vectors first and then applying a linear transformation is the same as applying a linear transformation first and summing the resultant vectors. Consider the vector space P2 of quadratic polynomials, and define the derivative operator as a transformation from P2 to P2. Using the usual definition from calculus, it is easy to see that the derivative operator is a linear transformation. Just as we can express any vector using its coefficients in column notation, we can express any linear transformation as a matrix operator. The derivative operator that maps P2 onto P2 is given by this matrix notation, in the usual monomial basis. Notice that by applying the derivative operator, we lose the x squared term. We are in fact mapping from all of P2 to a two-dimensional subspace of P2. This subspace is called the range, or the column space. The column space of the transformation A is an image of the vector space of V under the transformation A. It is a subspace of W. That is, it is a vector space subset of W. The dimension of the column space of A is called the rank of A. Recall that the rank is also equal to the number of pivots of a matrix. Let's consider the quadratic polynomials under the derivative operator. The column space of the derivative operator are degree 1 polynomials. In matrix representation, the right-hand side vector has a 0 in the first element, and arbitrary values in the second and third elements. So, the column space is the span of the vectors 0, 1, 0 and 0, 0, 1. The dimension of the quadratic polynomials is 3, but the rank of the derivative operator on the quadratic polynomials is 2. What happens to the other dimension? It is all sent to 0. The derivative operator sets all constant terms to 0. We lose that information, and can't get it back again uniquely. The vectors that are mapped by A to the 0 vector form a subspace of V called the null space or kernel of A. Trivially, if A is the 0 operator which maps everything to 0, then the null space of the 0 operator is all of V. If A is the identity operator, then the null space is only the 0 vector itself. The constants form the null space of the derivative operator. We can write the null space of the derivative operator succinctly as the span of the vector 1, or in matrix notation the span of the column vector 0, 0, 1. To conclude this lesson, let's summarize the key equivalence in linear algebra. The linear system Ax equals b has a unique solution for any vector b. The matrix A is invertible, and similarly, the matrix A transpose is invertible. The columns of A are linearly independent, and similarly, the rows of A are linearly independent. The null space contains only the 0 vector. The rank of A equals n. In later lessons, we'll see that equivalently, the determinant of A is non-zero, and that all the eigenvalues of A are also non-zero.